Hello and welcome to another one of these ADD videos. Today we're going to be looking at the conservation of mechanical energy. If you recall, work has two basic equations that we deal with. One was that the total work of motion is going to be equal to the change in the kinetic energy, and we're going to have the difference of the terminal point minus the initial point. Anytime you see this delta right here, make sure that you understand that that means the final minus initial. Okay, and if you forgot, kinetic energy is equal to 1/2 mv squared. We also know that the change in work due to gravity is negative the change in potential energy. And what in essence that does when you distribute that negative sign through is it just switches which one of these terms is negative. And if there are no other forces acting on it besides gravity, and you neglect the air resistance, you can equate these two changes in work and set the two equations equal to each other. When you do that, you're able to go through and come up with the work energy theorem. So we have here the change in work due to gravity is equal to the change in work due to kinetic energy, so it's going to be equal to the change in kinetic energy equals negative change in potential energy. And then at that point, if you plug in those formulas above, you get this and this. So what you want to do is you want to get the one subscripts on the same side and the two subscripts on the same side and do it to where they all become positive. Minimize your algebra. So then here, in this case, you would add that K1 to one side and add this U2 to the other side, potential energy. And you get the work energy theorem. All right? So again, this is if the only force acting on this is gravity and we neglect air resistance. So we refer to this potential energy, which is mass times gravity times height, plus the kinetic energy as the total mechanical energy. So if you hear that term, you know that that's what we're talking about. And if there are no other forces acting upon it, this is a constant. That's why you can set those two things equal to each other in the work energy theorem. All right? So when do we use the work energy theorem? We use it whenever we have curved motion problems, varying force problems, or both of them. Okay? So anytime you see that, just now sometimes whenever you deal with these problems, you will have a force besides gravity. All right? So whenever you have a force besides gravity, you have to incorporate that work done as well. So what happens if there's another force besides gravity? Well, we add this work other term here to the left side of the equation. So what it'll look like is it'll be the same work energy theorem, but on this side, initially, you're going to do some work. Let's say you're throwing a football or baseball, or something occurs to where force is applied that makes a work occur that we add on this side, and then this side stays the same. All right? So make sure you check out the example videos. Also, one other quick note, whenever we do have work besides gravity being done, then the mechanical energy is no longer constant. All right? It's only whenever the only force is gravity that it's constant. So make sure you check out the sample videos. Make sure you do as many of these as you can. As always, practice, practice, practice is the key to success. I hope I've eliminated any doubts that you might have enough to get started. Thank you and have a nice day.